So yeah, so like I said, my presentation is just on modeling problems with Python. Because of all this lockdown and whatnot, I've had like just some time just to explore some of these different Python libraries. So I'll just like talk you through two of them today. I wait, yeah, just two of them. The first would be Python MIP, and the second is Gecko. I think I used Gecko in my last presentation here to do some dynamic optimization. So I'll just like do an overview of that and like do a short overview of Python MIP just to show you like what you are probably missing out on if you haven't used these things yet. So yeah, so like I said, we just go through Python MIP and Gecko and just a short preamble on both. Right, so modeling with Python. So yeah, so I had more in my present view, but I can't remember, so I'm just going to read it off the slide, my bad. So yeah, so there have been a bunch of advancements with machine learning technology, and it's been accompanied by growth in a lot of different types of problems in a lot of different mathematical areas. So one of these key problems is optimization. This has been a problem for a while. I mean, who doesn't want to know how to save money or how to get to work faster or something like that? So, you know, innately humans, we like to have optimal solutions to everything that we do. So here's optimization, then there's dynamic optimization. So optimization mainly involves the minimization of some payout function or some yeah, let's just call it the payout function. I forgot the other name, but so yeah, so preferably the minimization, of course, be the maximization in some cases of some payout function, which respect to some state variables. So you could call it X in this case, and some other inputs. And these inputs could be like control parameters and disturbances, those types of things. So dynamic optimization takes it a step further and uses differential equations or it uses the differential equations of the state variables as state variables itself. So when you look at things like infectious diseases and whatnot, you don't really see people define a disease by the number of susceptible people at this moment. It tells you the overall rate of change of the number of susceptible people, or the rate of change of the recovered people, the rate of change of infected people, and so on and so on. So yeah, so this is what I was just saying. So you can have some constraint functions. We could call them f of x, u, and g of x, u, where our x is our state variables, our u is our inputs like control parameters and whatnot. So we can have constraints that's based on solely equalities. So we define some function f of x, u has to be such that it's equal to 0, or we can define it in terms of some function g of x, u, where it has to be in terms of an inequality, so like greater than some value, less than some value, something like that. So bring back to the idea of infectious diseases again, we could, for instance, if we, okay, so something that I'll do later on is in this, we have a social distancing parameter, or like a lockdown parameter, something to prevent the spread of a disease. So we will want to put a constraint on that so that there isn't like a total lockdown of an economy, because that would have in itself negative impacts on the whole country and whatnot. So let's say we want that 80 at maximum 80% of people can be locked down at any particular point in time, so that like only essential workers, how they have it right now in Trinidad, so only like really essential workers like healthcare workers and whatnot could be out at work. So that's an example of having a constraint as an inequality and whatnot. So yeah, right. So yeah, so modeling with Python. We have so we use algebraic modeling languages, or AMLs, to solve optimization problems with Python. Sorry, just going by the top of my head right now. Oh, this was pre-written down somewhere. So
hey,
yeah,
Jodhan.
Hi.
This is in PowerPoint. So my suggestion to you, and I have done this before, is pause for a couple of questions and transfer the slides to your phone, and then read off your phone, if it helps.
Okay, yeah, that's fine. But I was kind of enjoying the challenge of like trying to remember it all. But
All
yeah.
right, then keep killing it. You're doing good.
Okay, thanks, Tori. Yeah. Anyway, so we have algebraic modeling languages, and you could find a lot of these in Python. There's like SciPy, and there'll be the ones that talked about like Gecko and Python MIP that you'd use to solve these optimization problems. So we have so AMLs, algebraic modeling languages, facilitate the interface between advanced solvers and human users. So there's a lot going on at the back end that we won't particularly understand, but they save us a lot of time in terms of solving these problems, because even like simple problems, like is this one I'll show you, like the n queens problem, where you'll have an n by n chessboard and n chess queens on it, and you have to arrange them in a way that no queens can attack one another. So of course, if you're thinking like in terms of what am I trying to say? Yeah. So in terms of like a 2x2 board, that's impossible because there are only like so many spaces you could fit two queens, and you can't get that. But if you try to find like a massive number, like a 100 by 100 board, and you have to have 100 queens all across that board so that none of them could attack one another, that kind of number is pretty big for any one of us to just look at and be able to solve right away. But these AMLs tend to solve these very easily. So, okay. So AML simplifies solving complex optimization problems by allowing them to be expressed in simple and intuitive format. Such modeling languages are also able to accept and utilize constraints in order to optimize some control or input use. So that's like what I was saying with infectious diseases. So they're able to take in an input such as a social distancing parameter, quote unquote, and we could put some constraints on that. It can't be greater than 80% or 0.8 of the population, and it will work with that. It doesn't find any difficulty with that. But we know that if we were to introduce something like that into a simple problem, it'll make it a lot more complicated for us to solve. So in this way, what we look at is these two different Python packages, and we'll see that Python MIP is much better suited or designed for standard optimization problems, so nothing involving differential calculus, but Python Gecko is primarily built for solving dynamic optimization problems. So we look at three different problems with MIP. The first will be the traveling salesman problem. So that's like if you're in a neighborhood and you want to go from house to house, visiting one house only once, and you want to like minimize the distance and so the time taken to make your rounds. So like you could, in theory, let's see, more efficiently have a paper route or something like that. Or if you're in a different country and you want to travel around tourist attractions, you could easily like put this into code to run, and it will tell you the most efficient route to take. And then there's the n queens problem, which I already spoke about. If you have n chess queens arranged on an n by n size board, how do you arrange them so that no queen can capture one another? And then the last one is, right, the job scheduling problem. So if you're in a factory and you have like n jobs to be completed by m machines, I mean, simplest case is that you have the same number of machines and jobs, right? How do you schedule the machines so that the time taken to complete all jobs is minimized? Now, this could be, I think it's deceptively tricky when you think about it, because I mean, one solution for it is like you just let each machine go on its own, but we'll talk about that later down, right? So yeah, so traveling salesman. So I think this example from a text I saw online. So if you're in Belgium and you want to like visit some of the main tourist attractions, so you want to visit what places are in Belgium? I wasn't good at geography. I think Brussels and Antwerp and those types of places, right? So we have this map here, and we want to be able to visit all these places in Belgium only once, and we want to do it so that we travel the minimum distance in total. So what you do, you want to, well, the payout function will be this Cij by Xij. So what this is basically saying is that you just want to minimize the total distance on the whole. And you want to do this by only going to each destination once and leaving each destination once. So yeah, so I believe the code for this is written right here. So yeah, so you'll want to design an upper triangular matrix. There are 14 places on the map. So you want to upper triangular matrix. The first will be the distances of all places except Antwerp from Antwerp. So since Antwerp is the first place, the first distance will be the distance from, I'm not sure how to pronounce that, sorry, forgive my Belgium, but it's Bruges or Bruges, I'm not sure. And next will be Seamine and Dinant and those types of places. So yeah, so you want to first outline an upper triangular matrix given these distances. Then yeah, this I took straight from the example that I found it. I can do this on my own. But yeah, so these just outline the constraints. You only leave each city once. You want to minimize the objective function. You want to enter each city only once, and so on and so on. So once a solution is found, it produces the output, and this was the optimal path that it found. So given, wait, let me just go back. So given these distances of each city from each other, and they're just putting random distances, they're not exactly to what might be in reality. Yeah, but given those distances, you could go efficiently from place to place while entering each place once, except, well, Antwerp, because it starts at Antwerp. But if you enter and leave each place once, then you then the total distance, the total minimum distance will be 550 units, and this will be the route, the toll. So yeah, so yes, I did have to clip out these arrows in, but yeah. So if you start at Antwerp, you will go to, well, the next place, and then Ghent, and then Grand Palace of Brussels, and then Waterloo, and so on and so on. So that's just one example of how you can use Python MIP. And the next would be the n queens problem. So yeah, so we have, this isn't really, it's not a traditional optimization problem per se, because you're not trying to minimize anything, but you are trying to constrain the positions of these queens. So you don't want to have more than one in a row or diagonal or a column, because, well, you know how queens work on a chessboard, then they'll be able to capture one another. So those are the constraints that we have for this problem. And yeah, so the code for this, yeah. This was the code. I set the n of 37. I wanted 37 by 37 chessboard with 37 chess queens, and I wanted to put them, well, denoted them by zeros here, but yeah. So we have a 37 by 37 chessboard. This would be the solution. So if you have 37 queens, these will be the positions that you put them on. So no two queens are on the same diagonal, no two queens are in the same row, no two queens are in the same column at all. So, you know, problem solved, apparently. So if you ever have a problem like that, like you have to be in a classroom where there's a bunch of different students and there are a bunch of empty seats, and you don't want to like have two students next to each other or something like that, you could put like the number of students into one of these Python packages, and I'll be able to solve it for you and tell you exactly where to put them. So you won't have any two students next to each other fighting or something like that. Right, yeah. So the job scheduling problem. So this one was pretty interesting. I favored it the most because imagine if you're in a factory. So here there's only 3 jobs and 3 machines that you're using. So the time taken at each machine is given in the parentheses next to each M1, M2, M3, right? So it seems very simple, but deceptively difficult because at the same time, you have the constraints where you can't have one machine operating two jobs at the same time. So that's a given. You can't have something that's like if you're in a factory and you have to say have a machine that cuts blue cloth, cuts purple cloth and cuts red cloth, and then they have to stitch it and then they have to turn it into a top or something like that, right? You can't have the one that's cutting blue cloth. Well, what am I trying to say? You're right. You can't have one that's cutting blue cloth, stitch the blue cloth at the same time because the blue cloth has to, you know, be cut first before it's stitched. So you can't have them operating two different jobs at the same time. You also can't interrupt them while they're doing a job, and they must have a specific order to which they do the job. So say for job one, you're trying to make a blue top, perhaps machine three in this case would cut the blue cloth first and machine one would stitch it up. Then machine two would turn it into a blouse. And then job two would be making a red shirt. Machine two would be the one to cut and so on and so on. So, right. So yeah, so this was another example that I was playing around with a while ago. So yeah, so all you have to do is just put the times in the matrix that they're given in the initial problem here. So 2, 1, 2, 1, 2, 2, 1, 2, and 1. Then you put the machines, you could put them 1, 2, 3, started with 0. It doesn't really matter. And yeah, so it'll give you the completion time. So one of these solutions might be just to let machine one do all its tasks first and then let machine two do all its tasks, or perhaps you want to let job one be complete first and job two, then job three. But if we look at these times, if we let job one be completed first, that's let's see, that's 5 units of time. Then if we let job two be completed after that, that's another 5, and then job 3 is 4. So that's 14 units of time that's you're using already. But if you put this into the optimization software, then it could solve it and give you the most optimal solution. And the result is to let the jobs follow this pattern. So you let job 1 and machine 1 start at time 3, and those types of things. It's not in order. It's in order of the jobs with the outputs. I should have reordered it for this. My apologies. But yeah, but like I said, I was looking at an example from the documentation on this when I use this. So I got a diagrammatic of how the jobs are organized. And yeah, so instead of letting job 1 be completed first, then job 2, then job 3, you can have overlapping jobs with separate machines so that no machine does 2 things at once, but each job gets completed on the whole 7 units of time. So that's half of what the overall timing was given by before. Yeah, so to move on to Gecko now, which is pretty much like Python MIP, but it's more for, like I said, dynamic optimization. So yeah, so Gecko is an optimization software designed for solving differential algebraic equations. So rather than just having algebraic expressions, you have differential algebraic expressions. So it's equal for solvers for linear, quadratic, nonlinear programming, those types of things. So like I said, more aptly used for dynamic optimization. So my last presentation, I used Gecko to solve what's this? I was doing, sorry, lost my train of thought. Yeah, I used Gecko to solve an optimal control problem for an infectious disease because there was a problem I was working on before. And so I included that in here because I couldn't find too much examples on what people use Gecko with. But yeah, so here we have some infectious disease and we have these state parameters, S dot, E dot, I dot, and R dot. So these gives the rate of change of the different classes of the population. So S would be susceptible, and E would be the exposed, I would be the infected, and R would be the recovered. So we have the contact rate, which is beta, the recovery rate, which is gamma, infectivity rate, which is alpha. So that's the rate at which an exposed person becomes infectious. And we have a control U, which represents the amount of social distancing, lockdown, and other preventative measures. And I wrote measures twice there. Yeah. So, right. So using Gecko, just wanted to simulate it on a small population, because when you have a larger population, of course, it takes longer. And from my experience, when I tried to simulate it on Trinidad, which is about 1 point something million people, it took a couple hours to run. So I just wanted to get something quickly done. So yeah, so using an initial population, we have 100,000 people, and we use the reproductive rate of the disease COVID-19, which is 2.45, and we want to set a constraint on the amount of prevention that we can use. So let's say we want 80% of people at one time to be in lockdown. That's a constraint, simple as that. It could be 80%, it could be less than 80, it could be 0 for all we care, but we will get an optimal solution based on this. Yeah, so I didn't include the code for this because it's quite long, but if you look through the Gecko documentation, you'll be able to find examples of how people utilize this. Or if you want, you could probably send me an email afterwards and I can show you what I did. But yeah, so this is the curve for the number of infective exposed people for the modified model that we use. So at any instance in time, the number of infective people is less than or equal to 2%. And I believe the number of exposed people is less than or equal to 3.5%. So of course, we see that this takes a while longer to taper off than if you just leave it without having any control measures. So for instance, it reaches 0 at a roughly, well, not 0, close to 0 at about 200 days. But if we don't have any control parameters, it reaches 0 at around 140 days, I suppose. But in this way, we've managed to control the number of infective and exposed people, so there won't be things like a mass panic and whatnot like that. So I'm not sure if that's what they're using right now in Trinidad to tell us to have a state of emergency and keep us indoors, but one can believe, right? So yeah, so this gives the number of susceptible and recovered people at any particular instance in time. So we see that because of the control measures, the number of susceptible people, what am I trying to show here? Wait, sorry, yeah. So the number of susceptible people it tapers off less steeply. So it doesn't quite reach 0 at any particular point in time, but it also doesn't, sorry, losing my train of thought. But the number of recovered people as well, it also doesn't reach such a high maximum. But like I said, that's all because of this. Because introducing this control, we are able to keep the number of infective and exposed people to minimize them to some degree. We keep them below some certain percentage or whatnot that we wanted. So this is just a result of that. So we may have more susceptible people at any instant in time, but that's just a price to pay, because susceptible doesn't mean that you're infected. There's just more people that can get the disease at a particular point in time, but it doesn't mean that they get the disease. Yeah, and this shows the variation of the control parameter for the modified model. So you see that at first there's like no social distancing, no prevention and whatnot, and then it reaches a maximum of like 0.69 at a point, and then it tapers off and reaches 0 again. So maybe, just maybe, we won't be in this state of emergency for much longer. Yeah. So yeah, so I'll try to keep it short. Thank you for your time. And yeah, I think that's all I wanted to say. I hope you all enjoyed that. And if you all have time, just go through these optimization packages and libraries. There's a lot of different problems and different yeah, there's a lot of different types of problems that you could solve with them. There are a lot of different ones that I've experienced in my past that like during courses in UE, like discrete mathematics and these things that you'd have to solve by hand, but these things are built for solving them. And I worked some of them out and it was a lot easier than working it out by hand. So, so if you're interested in this type of stuff, you could look it up yourself. You could send me an email or something like that. And yeah, I hope you enjoyed the presentation. Thank you.
Thanks, thanks, Jodhan. Yeah, glad to see the interest in optimization. I guess a lot of people are focusing on machine learning, which is good, but optimization is also important, especially what you find locally in industry where you're trying to optimize processes, etc. If there's no data to do any kind of machine learning stuff, you end up having to use traditional optimization. So we have used it, quite a bit in the past. So for instance, Trisha uses dynamic programming for her work on OSNs. We had an interesting problem we worked on a couple years ago, published in a music journal, I believe. What I wanted to do is, given and I think I probably mentioned this in the past, but given a list of songs, find a sequence such that the transition from one song to the next is as pleasing as possible. Yeah, pleasing. Yeah, pleasing. Yeah. And that actually is a TSP, a traveling salesman problem, because basically you're going to have a distance between each pair of songs, and you want to go from song to song, traverse all songs, such that the total distance travel is minimized. So it is exactly the traveling salesman problem. So
that's pretty interesting to look at it. I mean, probably something I could do for my next TT Lab presentation.
Yeah, you can have a look at it. Well, Sterling did this a while back. Actually, we started this off. We started this off when we were doing some work for this streaming soca streaming company, and they wanted to replace some of their playlists that were generated by DJs. They wanted to automate that process, so our TT Lab member was working on that. He didn't complete it, but we ended up working on this playlist sequencing problem, which was interesting as well. But the point I'm trying to make is that you'll come across problems that may not look like a TSP or a bin packing problem, etc. And it helps. In fact, today I had a discussion with another TT Lab member. We are working on something where you require bin packing as well as optimal scheduling. So it's a combination of scheduling and packing. A very interesting problem as well, and this is a real world problem we're looking at. Something else came up recently that requires optimization. I forget what it is, but anyway, the point is that optimization is important. It's a wide area. You can spend full courses on each aspect of it: nonlinear, stochastic, dynamic, integer, etc. So thanks for highlighting it, Jodhan.
Yeah, it's no problem. I think like when I came in today, you're talking to Tariq about the scheduling with optimization and whatnot. And I was like, oh, look at that, coincides with what I'm doing today.
Yeah, actually, a lot of my work in the old when I was in wireless was on scheduling, optimal scheduling for wireless communications.
I was reading up on that because when I was doing some research for this, I saw this research paper that did like optimal scheduling with some wireless stations, and they had them organized in like hexagonal grids and whatnot.
So it is a complicated, because you're working in 3 dimensions. space, time, and frequency. And so you have to optimize for quality of service, etc. So it's a really interesting problem. I haven't done anything on that, for a while, but yeah. All right, thanks again, Jordan.
Yeah, no problem, Prof. That's it. Anybody has any questions? Torian, I know you always have something to say.
Okay, so I've got.
Oh, I can't really hear you, man. You sound very faint.
Okay. So how did you handle multiple solutions? Do you have any thoughts on reducing on a
Bring the mic closer, man.
Yeah, can't really.
You're speaking away from your phone, Torian.
Give me 30 seconds.
Okay, sure.
I think he said if there was the ability for these software guests to have alternate solutions. I think that's what I heard.
Oh, okay.
That's it.
Yeah, I mean, I guess that's completely admissible, but I've never experienced it. Although, just mind you, my experience with this is quite limited. I don't have years of experience doing these things like Prof. But yeah, this was just something that I'm passionate about, and I like optimization, and I just looked at a bunch of problems while I was on lockdown. Well, still am, and thought of putting them together in a presentation. But yes, the possibility of having multiple solutions is likely. But okay, so like I think it's something that we all should be familiar with. It's like I forgot what they call it, but it's kind of like a scheduling problem. But you try to find like the shortest distance between 2 points, but you have to move from one point to the next, and there's this whole network of points and whatnot. And those tend to have multiple solutions. Like I was doing an exam a while ago, and it had like 4 different ones. So yeah, so those things tend to happen at times. Still can't hear you if you're talking to Ryan.
Okay, you should be able to hear me a little bit better now.
Yeah, a little bit.
All right, cool. Okay, so yeah, no, it wasn't just like, I know many optimization problems come with multiple solutions, but is there a way, how many of these, so, and I guess this comes to the second question is,
Yeah, you
have
dropped off.
you want to have multiple solutions, or able to see all your solutions. Like, so I want to see my solution set of solutions so that I can A, pick, right? And then B, the second question is, what's the time taken to get some of these solutions? Because some of these may not be like the most optimized way to get them, but like,
Right. Yeah.
at some of these some of these kind of do look brute force, but
Mhm.
when things are small, that's okay, right? Because the computer takes
Yeah.
up most of the time, and it's not you doing the work. But then after a while, it gets rather large. Have you looked into any research on optimizing the optimization?
No, I haven't looked into that research, but the time taken to do these sorts of computations that I've presented here is very short. I don't believe anything took longer than a couple of seconds. Of course, when you go more into like the dynamic optimization ones, those could get pretty complicated. Like I did a model for infectious disease that included a lot more different control parameters. So there's like a latency time, an incubation time for the disease, those types of things. So those factors, so accounting for those factors as well as increasing the population size made it so that it took quite a while to solve. So I think offhand, like I was trying to adapt it to Trinidad and Tobago and I think I did that last time, but that took like about 2 hours to do. And I was trying to do it to like a country like the United States, which has, orders of not just millions, but like hundreds, millions to billions of people in there. And after the code had passed for about an hour, it got an error and it said something about I can't remember exactly what it says, but basically it had too much to work with so that it can finish. So So that's something interesting that you brought up, looking into optimizing the optimization software. But no, it's not something that I've looked at yet.
Well, interesting point on that, like that it kind of reminded me of. We were looking at using D-Wave, which is a quantum computer, and how do you program it to actually solve extreme.
Hmm. Okay, you fell off there. Can't hear anything.
You can do it with quantum, some of these larger problem sets, but you just have to learn how to program it, which is kind of
Yeah.
interesting how they had to do a change version. Plus, we won't get into why GPUs are also kind of good, but that's okay. So then the last one is so since you can predict when we're getting out of state of emergency, can you just tell us when it's going to happen for those of us who are stocking up on necessities like rum?
What is that?
Since you can predict what's going to happen and when the end of the state of emergency is going to be, can you tell us so that like we can
No.
figure out when we're getting rum?
I can't say that at all. In the last presentation I did, I think that was something that I brought up too, because I tried to make it as much like Trinidad as possible, and it was grossly exaggerated in my opinion. Probably I got some of the parameters wrong, the reproductive rate of the disease, the incubation time for the disease, those types of things. But it showed like there was a sudden spike of like the order of like at least tens of thousands by day 500, 600 or so. So that's almost like 2 years after, well, a year and plus after the disease, the whole pandemic started. And when they announced the state of emergency, I messaged Nicholas. I was like, I talked about this before, and I think it's quite interesting that they bring it up now. But yeah, so I mean, I never thought that it would reach like this, and the model isn't exactly right at all, but well, not 100% right. It's right given what I gave it, but I couldn't have.
You need to give it more because you didn't
Yeah.
add in variance, man.
Yeah, and like
Very
people coming in from external sources, people dying, those types of things. Yeah. Also put a constraint to like minimize the death rate so that nobody would die. But that just so that made
Live in
it
a
so that
dream world, sir.
yeah, I know, but that made it so that like 0 people died at a point. But yeah, so it's just it's a lot of different things. These things get more complicated as you look into them, and I mean, I would like to do more work with this in the future, but it's very time consuming to be able to think of these things far less to code them. Yeah.
Yeah, no, that's true. All right, done harassing you. Thanks again, and I loved your presentation slides. Very nice design.
Yeah, thanks, Torin.
Hey, Jodhan, just one question. I was wondering if by chance you'd come across or tried anything on the Julia side of things, and
No.
like as a comparison between Gecko and Jump.
No, I've never used anything with Julia, to be honest. Yeah, when I was doing dynamic optimization in the past, a lot of people told me use MATLAB. I was like, no. And then a lot of people told me try Maple, and that wasn't working out as well. So after Python seems so easy to use compared to those, so I just never bothered trying anything else. But yeah, I guess Julia might be a try. Yeah.
Okay. I'm on the GitHub for Gecko right now, and I was looking at the code content, and it seems like the key parts of it, or some key parts of it, were written in MATLAB, and it just has a Python wrapper around it.
Mm-hmm. Yeah. Because
Julia,
I think you could
would be much more approachable.
Yeah. Okay, I'll look into that. I've never what's the word? I never thought of using Julia, to be honest. Yeah, I'll make a note.
Yeah.
Yeah.
One would argue that this is kind of like the stuff Julia was made for, but that's more fight that I guess Inzamam would probably fight, not me.
Well, we actually use Julia for our optimization course. Well, it's a applied operations research course, but yeah, we use Julian for that.
Yeah, the library Jump, I know Inzi is a big fan of, and what comparing to the GitHub that I'm seeing for Gecko,
Mm-hmm.
yeah, I would just briefly look at Julia, see what you think.
Okay, cool. I'll make a note. All right.